In this presentation, we will discuss magnetic properties of minerals. Magnetism is a very intrinsic property of matter, so basic that we have all seen magnets, lived inside a magnetic field, and have reaped the benefits of magnets ranging from navigational compasses to modern day generators and motors. The exact causes of magnetism include incredibly sophisticated interactions at the atomic level, but the effects can be studied microscopically. So, from our daily experiences, we get the notion that magnetism is somewhat related to iron content. It is related to iron content, but magnetism is not just iron content. Iron happens to be the most common mineral around us which is strongly attracted to magnets. Also, minerals containing iron are generally magnetic, but magnetic minerals do not necessarily contain iron. And in all cases, the degree of magnetism does not depend on iron content. In fact, minerals show a range of magnetic behavior, ranging from highly magnetic behavior like that of magnetite and pyrrhorite, and moderately magnetic behavior of sideronite and chromite, to weakly magnetic behavior as in tourmaline and monazite, and even non-magnetic behavior like in quartz and calcite. Magnetism is also used in ore dressing to separate magnetic minerals from non-magnetic ones. It is the electromagnetic separation technique which is commonly used to separate magnetite from agate. Also, large quantities of magnetic materials like magnetite cause measurable variations in the magnetic field of the Earth in that region. These variations can be detected by magnetometer and is hence used to locate large bodies of magnetite. Magnetism is also the underlying principle in paleomagnetism, and this field of study has revealed some startling discoveries about Earth's magnetism. Any magnetic field points from magnetic south pole to magnetic north pole, and so the magnetic field of Earth has different orientations and intensity on different parts of the planet. As molten basaltic magma cools to form new rocks on Earth's surface, iron-bearing minerals in the magma get aligned in the direction of the magnetic field that exists when the magma cools. But after solidification, the particles are unable to move further. This means that the magma records the orientation of Earth's magnetic field at the time of its cooling, and the study of such records is called paleomagnetism. Digging through these paleomagnetic records, geologists have found that the magnetic alignment of some layers of rocks is opposite as that of one on the top, and these alterations in magnetic alignment happens quite a lot of times as we dig deeper. These observations have led geologists to conclude that Earth reverses its polarity every 300,000 years. This means that the magnetic needle, which today points towards the north, will point towards south after magnetic pole reversal. The last reversal, called the Bruhnes-Matuyama reversal, happened about 800,000 years ago, which means that a reversal is due in the next couple of thousand years. Not only this, paleomagnetism has been used to confirm the theory of seafloor spreading. Along the oceanic ridges, we find striations of rocks containing oppositely magnetized rocks, and this pattern becomes symmetric about the ridge crest, which helps us to find it. These magnetic variations may be then used to also predict the age of the seafloor and also to measure the rate of seafloor spreading. The theory of seafloor spreading also led to the proposition of the theory of continental drift, which tells us that continents are not static land masses on the face of Earth, but are rather dynamic structures which move and also grow and shrink through the forces originating from the mantle. Magnetic records have been thus used to unravel the reversal of Earth's polarity and count as evidence to the seafloor spreading and continental drift theory. Thus, magnetic properties of minerals play an important role in geological studies. This concludes magnetism. Thank you.